Right now, whatever you're looking at, the screen, the wall behind it, your own hand, you think you're seeing color? You're not. You're seeing your brain's guess about what's out there, built from almost no information. The red of a fire truck and the red of a sunset can be made from completely different mixtures of light, physically, measurably different, and your brain will call them the same color. It doesn't care. It's not trying to show you what's real. It's trying to show you what's useful. And here's the thing that gets me. The reason any of this works at all, the reason there are specific wavelengths of light to detect in the first place, is quantum mechanics. Take away quantum physics, and there are no sharp spectral lines, no discrete colors for eyes to evolve around, there's just a blur. So we've got two problems here, and most people confuse them. Problem one. The light out there in the world really does have specific wavelengths, and those wavelengths come from quantum mechanics, from electrons jumping between discrete energy levels inside atoms. That part is real, that part is physics. Problem two, your brain takes that information and throws most of it away and then invents an experience, the experience of red, of blue, that exists nowhere except inside your skull. That part is neuroscience. And the reason this whole topic fascinates me is that neither part alone gives you color. You need both. You need quantum mechanics to make the light, and you need a brain to make the color. And those are very different things. Let me show you what I mean. Hold your hand up. Look at it. See that color? The pinkish whatever it is of your skin? Now here's what's actually happening. Photons, little packets of electromagnetic energy, are bouncing off the atoms in your skin and entering your eye. Those photons don't have a color. They have a wavelength, or rather they have a frequency. And that frequency is related to their energy by a beautifully simple equation. E equals h times f. Planck's constant times the frequency. That's it. The photon doesn't know it's pink. It doesn't know anything. It's a vibration of the electromagnetic field carrying a specific amount of energy. And your skin is reflecting a whole mess of different wavelengths at once, a broad, complicated spectrum. Your eye catches that mess, and your brain, using just 3 types of sensors, turns it into a single, unified, confident experience. That's my hand, and it's this color. 3 sensors for the entire visible spectrum. Think about that. You're listening to a full orchestra through 3 microphones, and your brain is reconstructing the whole concert, but that's not the strange part. The strange part is what happens before the light gets to your eye, before your brain does its creative editing. Where does the light come from in the first place? Why does sodium glow yellow and neon glow red and mercury glow bluish white? Why do different elements produce different colors? This is where Newton comes in, and then where Newton stops and quantum mechanics takes over. In 1666, Isaac Newton did something that seems simple, but was actually revolutionary. He took a glass prism, set it in a beam of sunlight coming through a hole in his window shutter, and watched white light fan out into a rainbow. That alone wasn't new. People had seen rainbows in prisms before. What Newton did next was the crucial part. He took one color from that rainbow, just the red, isolated through a small hole in a board, and passed it through a second prism. And the red stayed red. It didn't break down further. It didn't change. He called this his experimentum crucis, the decisive experiment. It proved that white light isn't pure. It's a mixture. The colors were already in the white light, and the prism simply separated them. The prism didn't create anything. It revealed what was already there. Beautiful result. But Newton couldn't answer the next question, the deeper one. Why does heated sodium produce yellow light at exactly 589 nanometers? Why not 590? Why not a smooth spread of every wavelength? Why are the colors of the elements so specific, so sharp, so reliable that you can use them like fingerprints? For 200 years, nobody could answer that. And then in the early 20th century, the answer arrived, and it was strange. Here's what happens inside an atom, and I want you to picture this, really picture it. You're shrunk down, impossibly small, and you're sitting inside a sodium atom, watching a single electron. This electron is trapped. It's bound to the nucleus by the electromagnetic force, and it can't just be anywhere it likes. It's stuck in specific orbits, specific energy levels, like a ball on a staircase. It can be on this step or that step, but never between steps. That's the quantum part. The quantum in quantum mechanics literally means discrete amount. Nature doesn't let the electron slide smoothly from one energy to another. It jumps. Now imagine someone heats the atom, adds energy. The electron absorbs that energy and jumps up to a higher step. But it doesn't want to stay there. That higher step is unstable, so it falls back down. And when it falls, it has to get rid of the extra energy. How? It emits a photon, a single particle of light, carrying exactly the energy difference between the two steps, not approximately, exactly. And because the energy of a photon determines its frequency, and frequency determines wavelength, that photon comes out with one precise wavelength. For sodium, the big transition happens to produce light at 589 nanometers. Yellow, always yellow. Every sodium atom in the universe, heated the same way, produces the same yellow. See, that's what Newton was looking at when he saw colors in his prism. He was seeing the quantum structure of atoms. He just didn't know it. Every color of light that exists in nature is a message from the quantum world. It's an electron telling you, I just jumped from here to here, and this is the energy difference. The light isn't colored, but it carries information, a specific frequency that was determined by quantum mechanics, by the discrete energy levels of the atom that emitted it. And this is why I say quantum physics makes the light. Without quantized energy levels, atoms would radiate a smooth, continuous spectrum, every wavelength at once. No structure, no sharp lines. The universe would glow with a featureless haze. There would be no specific wavelengths for eyes to latch onto, no patterns, no information worth detecting. It's the quantum structure of matter that gives light its specificity, and that specificity is what makes vision possible. But now let me flip the whole thing around, because that was the physics. Now comes the neuroscience. And the neuroscience is, if anything, even stranger. That light, those precise quantum-determined wavelengths, enters your eye and hits your retina. And your retina is honestly an embarrassment. I mean that with respect. For all the beauty of quantum mechanics producing this incredibly rich, detailed spectrum of light, your eye throws away almost all of it. You have three types of color-sensing cells, cone cells in your retina. Three. They're called S, M, and L cones, short, medium, and long wavelength. The S cones peak their sensitivity around 420 nanometers, what you'd call violet blue. The M cones peak around 530 nanometers, green. And the L cones peak around 560 nanometers, which isn't even red. It's more like yellow-green. You don't have a red sensor. Let that sink in. The thing you call red, you don't have a cone that peaks at red wavelengths. Your brain infers red from the relative activation of the L and M cones. Now, each of these cones doesn't detect a single wavelength. It responds to a broad range of wavelengths, with a peak in the middle and tails falling off on either side. And the ranges overlap significantly. So when a photon of, say, 550 nanometers hits your retina, it activates both the M cones and the L cones to some degree. Your brain gets a signal, a ratio of activation across the three cone types, and from that ratio it constructs a color, not detects. Constructs. Here's a thought experiment that should bother you. Imagine I show you two patches of light. One is pure spectral yellow, light at exactly 580 nanometers, a single wavelength coming from, say, a sodium lamp. The other is a mixture. I've combined red light at 640 nanometers and green light at 540 nanometers. No yellow photons at all. Physically, these two patches are completely different. One has a single wavelength. The other has two wavelengths with a gap between them. Put them through a spectrometer, and you'd see they're nothing alike. But you can't tell them apart to you. They look identical, same yellow. This phenomenon is called metamerism, and it's not a flaw. It's a feature of how your visual system works. Because you only have three types of sensors, many different physical spectra can produce the same triple of cone responses. Your brain maps an infinite dimensional space, the full spectrum, down to a three-dimensional space. It's a massive compression. Most of the information is lost. And your conscious experience of yellow is just a point in that compressed three-dimensional map. It tells you something about the light, but it doesn't tell you what the light actually is. You're thinking, okay, but isn't it close enough? Doesn't it work? And yes, it works brilliantly for survival. You can tell ripe fruit from unripe, healthy skin from sick, predator from background. Evolution didn't build your eyes to do physics. It built them to keep you alive. But close enough for survival and accurate representation of reality are not the same thing, not even close. And if you want to understand what color actually is, you have to accept that the experience of red, the redness of red, exists in exactly one place in your brain, not out there. Now, I know how that sounds. It sounds philosophical, airy, maybe a little like something you'd hear at a dinner party from someone who's had too much wine. Colors aren't real, man. But I'm not saying that. I'm saying something much more specific. And Edwin Land proved it in the most dramatic way I know. Land, you might know him as the founder of Polaroid, did an experiment in 1959 that still bothers people. Here's what he did. He took two black and white photographs of the same scene, a still life with fruits, fabrics, colored objects. For one photo, he used a red filter over the lens. For the other, he used a green filter. So he had two transparencies, each recording the scene's brightness as seen through a different filter. Then he projected them onto a screen overlapping perfectly. The red filter slide was projected through a red filter, and the green filter slide was projected, this is the crucial part, with no filter at all, just plain white light from the projector. Now think about what's hitting the screen. You've got red light from one projector and white light from the other. Physically, the only wavelengths reaching your eye are red and white, which means you should see at most shades of pink and red and pale wash. That's what additive color mixing predicts, but that's not what people saw. They saw blues, greens, yellows, browns, a rich, full-color image from light that contained no blue wavelengths and no green wavelengths. The colors were physically absent from the light, but the observer's brains constructed them anyway. This is the Retinex theory, retina plus cortex. Land showed that your brain doesn't just read the wavelengths arriving at each point on your retina. It compares every part of the scene to every other part. It looks at the relationships, the ratios of long wavelength to short wavelength light across the entire visual field. And from those relationships, it builds a color map. The color you see at any point depends on the constructs, on everything else in the scene. Your brain is doing computation. Heavy, sophisticated, interpretive computation, and the output of that computation is what you experience as color. You're not a camera. A camera records what's there. You're a storyteller. Your brain takes fragments, incomplete, ambiguous, three-channel fragments, and constructs a vivid, seamless, confident narrative. And that narrative is color. You're thinking, okay, Feynman, you're saying color is just in our heads, and quantum physics makes the light, and these are two separate things, but doesn't that mean color is arbitrary? Couldn't evolution have wired us to see anything? And you're not wrong to think that. But here's where it breaks down. Color isn't arbitrary. It's constrained. The reason your three cone types are tuned to the wavelengths they're tuned to, 420, 530, 560 nanometers, isn't random. Those wavelengths correspond to regions of the solar spectrum where there's a lot of photon flux. Your cones evolved to catch the light that's actually there. And the light that's actually there is determined by quantum mechanics, by the energy transitions in the hydrogen and helium and other elements that make up the sun, filtered through the molecular absorption bands of the atmosphere. So quantum mechanics shapes the spectrum of available light. Evolution shapes the sensors to match that spectrum. And the brain constructs an experience, color, that maps the quantum information onto something a conscious being can use. Each link in that chain is necessary. No quantum mechanics, no specific wavelengths, no selective pressure for tuned sensors, no color experience. The whole thing is a chain, from quantum energy levels in atoms to photons to cone cells to neural computation to conscious experience. And color is the output of that entire chain, not any single link. But here's what gets me, and I mean this. This is the part that genuinely bothers me. We understand every link in that chain up to the last one. We can write the Schrödinger equation for the electron transitions. We can calculate the emission spectra. We can measure the cone sensitivities. We can even map the neural pathways from retina to visual cortex. We can explain why certain wavelengths activate certain neurons. But we cannot explain why the activation of those neurons feels like red. We can explain why your brain categorizes 640 nanometer light differently from 480 nanometer light. We can explain the computation, but we cannot explain why there is an experience attached to that computation. Why it isn't just information processing in the dark, neurons firing in patterns, signals being routed, outputs being generated, all without anyone home to experience it. That gap between the physics of light and the experience of color is the hardest problem I know. And I don't say that lightly. I've worked on quantum electrodynamics, which has some pretty hard problems, but at least in QED, we know what kind of answer we're looking for. With consciousness, with the question of why red feels like something, I'm not sure we even know what kind of answer would count. Let me give you one more thought experiment, and then I want to ask you something. Imagine a universe identical to ours in every physical respect. Same atoms, same quantum mechanics, same photons bouncing around, same evolution-producing creatures with eyes and brains. But in this universe, there is no consciousness, no experience. The creatures process information, respond to stimuli, avoid predators, find food, but nothing feels like anything to them. They're biological machines, running the computations but with no inner light. In that universe does color exist. The photons are there. The wavelengths are there. The quantum mechanics is there. Everything we've talked about, the energy transitions, the discrete spectral lines, the cone absorptions, the neural processing, all of it happens, but nobody is home to see red. Nobody experiences blue. The word color doesn't even arise, because color isn't a property of light, it's a property of experience. Now you might say, Feynman, you're getting philosophical again, and maybe I am, but I'm a physicist and I'll tell you what strikes me about this as a physicist. In physics, we talk about observables, things you can measure, and we got very comfortable in quantum mechanics with the idea that certain properties of a system don't exist until they're measured. A photon doesn't have a definite polarization until you put a polarizer in its path. An electron doesn't have a definite position until you detect it somewhere. Measurement in quantum mechanics isn't passive, it creates the outcome. And here with color, we have something analogous, not identical. I don't want to push the analogy too hard, because that road leads to mystical nonsense, and I'm not interested in mystical nonsense, but there is a structural similarity. The experience of color doesn't exist until a conscious observer interacts with the light. The light carries information, quantum-determined, precise, physical information, but the color is generated at the moment of observation, by the observer. That's not mysticism. It's just what happens. And it should make you at least a little uncomfortable, because it means the world you see is not the world that is, not because your senses are broken, because seeing is by its nature an act of construction. Your brain takes quantum information and builds a world of color that doesn't exist outside the building. Now, there's one piece of this I still can't quite settle in my own mind, and I want to know if it bothers you too. We know that different animals have different color experiences. A mantis shrimp has 16 types of color receptors compared to our 3. Birds have 4. Many mammals have only 2. A bee can see ultraviolet that you and I are completely blind to. So the color world each creature inhabits is different, even though the underlying physics, the quantum mechanics, the photon wavelengths, is the same for all of them. Here's my question. If I could somehow experience what a mantis shrimp sees, if I could plug into its 16-channel visual system, would I experience colors I've never seen before? Not combinations of colors I already know, not more detailed versions of red and blue, but genuinely new categories of experience. Colors that are as different from red as red is from the sound of a trumpet? Or is my brain so locked into its 3-channel architecture that it would just map everything into the same old palette, the same way it maps different physical spectra into the same yellow? I don't know the answer. Nobody does. And it's not even clear what experiment you'd run to find out. Because the question isn't about physics, and it isn't about neuroscience, it's about the nature of conscious experience itself. And that's a question physics hasn't even begun to touch. There's another piece to this. What happens when you follow the quantum mechanics of light all the way down, past emission and absorption, into the full theory of quantum electrodynamics, where light and matter become two faces of the same interaction? And I think that deserves its own conversation. But for now, I'll leave you with this. The next time you see a sunset, really see one, with all those reds and golds bleeding into purple. Remember that what you're watching is your brain's interpretation of quantum energy transitions happening 93 million miles away, filtered through an atmosphere, compressed through 3 types of cells, and assembled into an experience that exists nowhere in the physical world except inside your own skull. And it's still the most beautiful thing you've ever seen.